One of the greatest obstacles to crafting health and wellness is identifying and controlling inflammation. It's at the core of all complex and chronic diseases, and it's the driving mechanism that underlies the most common symptoms that people like you struggle to overcome. Join us as we explore cutting-edge science and research to give you the information and tools you need to create the quality of life you want and deserve. And now, here is the host of Inflammation Nation, Dr. Stephen Noseworthy.
Welcome back to what will be the final episode in our little mini-series on hormones and health. And today we're going to close out this discussion on hormones by looking at two final thoughts. And one is the idea of hormone resistance patterns. And then we're going to talk, as I mentioned in the last episode, about neurotransmitters and how neurotransmitters and hormones can actually work together in what we might consider functional pairs. But let's talk about resistance patterns first. I've mentioned this a couple of times throughout the series, but it's, I think, worth mentioning because there are many circumstances where people have very obvious signs of hormone imbalances, signs and symptoms, and yet their testing is normal. Now, one reason might be that perhaps whoever ordered the test didn't look at the right type of testing. Maybe they looked in blood when they should have looked in saliva, or vice versa. Maybe they didn't understand the difference between the impact of being on bioidentical versus synthetic hormones and how that might impact your diagnostic choices. Maybe they just didn't simply do enough markers. But it is possible that you actually truly might have a normal amount of a given hormone in your system and yet still not get all of the function that hormone should supply for you. And in that case, we call that a resistance syndrome. And perhaps the most well-known aspect or type of that is insulin resistance, where you actually have very high levels of insulin, but insulin doesn't work because the cell is not responding. And this idea of a receptor-based dysfunction is consistent with all receptor-based systems. And it will actually become relevant in our discussion about neurotransmitters as well, because whenever you have function that is conferred by activation of a receptor, by whatever plugs into that receptor, then having too much of that thing can cause the receptor to downregulate. You get fewer receptors, and the ones that are there don't work as efficiently. And so don't necessarily be disheartened or confused if you are talking to a doctor about your hormones and you have all the symptoms in the world that relate to that hormone, but they tell you everything is normal. Maybe the fault, again, was in the choice of diagnostic testing or incomplete testing, or maybe the problem is you have a receptor-based issue, which then brings us into the discussion about neurotransmitters. Because as it turns out, a lot of the hormones and neurotransmitters have functional relationships to the point where they are mutually supportive. And part of that relationship is in sensitizing receptors to be able to respond to an adequate stimulation for a hormone that's in circulation and available for the cell to take up and use. But before we get into that, let's talk about let's go through a basic primer on neurotransmitters, just give you a little bit of background. And this is kind of a watered down version of things that I've taught for, I don't know, the last 13 years or so in our functional medicine seminars, in teaching doctors about this. And this is an area that is of tremendous tremendous interest, just because we have so many clients that do have brain-based complaints, whether that is anxiety or depression or brain fog or focus and concentration issues or changes in memory function. So the first thing to know is that neurotransmitters function just like hormones do. In order for example, serotonin or dopamine to work in your brain, not only do you have to have enough of it, but you have to be able to plug into a serotonin receptor or a dopamine receptor to mediate the function. It's actually the activation of the receptor and not necessarily the neurotransmitter or the hormone itself that actually does the work. And so if you have variations in receptor populations, or if you have things that interfere with how the receptors work, or maybe you have some kind of a genetic polymorphism, which many of us do, I would suggest all of us do to some degree, many of which don't create any functional symptoms that we're aware of. But maybe you have a persistent problem because there's a just kind of bad genetic code that says that your receptors for a certain type of hormone or neurotransmitter don't work as efficiently as possible. But the bottom line is this: when it comes to function, relating to hormones and neurotransmitters, there's a lot of things that go into how that system works. But ultimately, at the end of the day, it's all about receptor activation. Now, just like we can have different estrogen receptor types, there's alpha and beta, for example. There are about 5 different types of serotonin receptors. There are multiple types of dopamine receptors. And so both serotonin, dopamine, and all of the other major neurotransmitters that we might mention can play different roles in different places in your body and in your brain just based on the attributes of the receptor that it's interacting with. And so we can't necessarily say that serotonin does only one thing. That's far too simplistic. Serotonin does whatever the receptor that it binds to determines, and that might be to increase function in some areas and decrease function in others. And so it's a receptor-based system, and it's all about receptor activation. Of course, neurotransmitters are the primary signaling molecules of the brain, but the brain does have receptors for inflammatory cytokines or immune-based chemicals. It also has receptors for different hormones, of course. I think we've covered that just briefly in other episodes. But in order to have, and let's just talk about neurotransmitters specifically, in order to have adequate function, we have to have good supply of a neurotransmitter, and we have to have the neurotransmitter receptor functioning normally. You have to have both. And so, for example, if someone wants to take or is prescribed a serotonin reuptake inhibitor, an SSRI, as they're commonly called, that does increase the supply of the neurotransmitter, but that doesn't guarantee that function is going to improve, because function is not necessarily just related to the amount of neurotransmitter that's available. Again, it comes down to the receptor. And, ideally, we'd be able to identify, we'd be able to identify the different variables that affect how the receptors actually work. And if you look at the neurological literature, just look at basic neuroscience, there are 2 types of modulation. We can kind of broadly classify the things that modulate the receptor site sensitivity, if you will, and their activity by classifying them as either homotropic or heterotropic. And those are fancy words that you don't really need to remember, but here's the basic delineation between the two of those. Homotropic modulation is where the neuron that makes the neurotransmitter that wants to send a signal to another neuron actually modifies itself. So the more that a neuron sends a signal to the next neuron in a line or in a sequence, the more that happens, the more the system modulates its own activity to prevent overactivation. And this is something that is important, because when a brain or a neural pathway or a region of the brain becomes hyperexcitable, that leads to states of dysfunction and potentially states of degeneration, as function tends to outpace its metabolic supply and its energy production demands and capacity. So this is just a feature, and this is actually one of the reasons why reuptake inhibiting type drugs quite often have a short period of what we call a honeymoon phase, where things get better for a period of time, but then they stop working when nothing else has changed. And this is through homotropic modulation, meaning if the system senses that there's a lot more neurotransmitter available, it might work better for a period, but then it goes, okay, this is way too much. We need to downregulate our receptor site sensitivity. Let's take away some receptors, because we don't need to get overstimulated, because that's not a normal state of physiology. And this is perhaps the most common feature, or perhaps the downside of using things like SSRI medications or reuptake inhibitors for other neurotransmitters like dopamine or norepinephrine, is that for most people, there's just that honeymoon phase, and then things don't work anymore. And so you end up in the cycle of increasing the dose to get function stops, and then increasing the dose, and so on, and so on, and so on. And now, so that's how the system modulates itself. It's a self-protective mechanism. There's a whole other class of modulating properties or variables, and that would be things that are considered heterotropic. And that means something outside of the system is affecting the function. And that might be inflammation. It might be the presence of stress hormones or stress chemistry. And again, many different factors that can affect this. But the key concept for the purpose of this little mini-series is to focus in on the fact that hormones and neurotransmitters work in these synergistic pairs with a somewhat bidirectional relationship of mutual support. Now, I'll outline those very briefly just here in a second, but understand that for neurotransmitters, certain hormones are heterotropic modulators. For example, thyroid hormones sensitize all neurotransmitter receptor sites. And this is one of the reasons why people with thyroid issues, particularly Hashimoto's hypothyroidism, where the immune system's not being controlled and contained, that people with thyroid issues tend to have bad brains, especially if they have really poorly controlled immune mechanics. It's simply because, and there's other mechanisms like the general inflammatory state that can break down the blood-brain barrier and cause neuroinflammation. But at least at one simplistic level, if you have thyroid hormone insufficiency, then you lose one of the major contributors to neurotransmitter sensitivity at the receptor site. And it's across all receptor site subtypes. And again, this is why one of the reasons why we typically see bad brains with people who have poorly controlled thyroid issues and, more importantly, the Hashimoto's hypothyroidism type, which is almost all of them anyways. So thyroid affects all neurotransmitters, but there is this functional pair link between, for example, estrogen and serotonin, and it is bidirectional, but we're focusing on neurotransmitters and how they affect estrogen receptors. And so what we know is that you might have a lady, for example, most people taking estrogen would be females, of course, and they may be taking or making an adequate amount of estrogen. They may have normal receptors in terms of population and otherwise sensitivity. But if something causes a serotonin deficiency, then serotonin is not available as a heterotropic modulator that actually improves estrogenic responses. And so maybe your estrogen symptoms are not coming from the fact that despite making enough or maybe taking it in some kind of a hormone replacement form, maybe it's not the fact that your levels are still too low, or maybe they're not in the optimal range. Maybe the problem's in a totally different system that has an impact on how your estrogen system works. We'll talk here in a second about how you might recognize that you have an issue with serotonin. And the same type of relationship happens or occurs between progesterone and GABA. And GABA is, of course, known as your primary inhibitory neurotransmitter. It kind of keeps check on everything so that neurological pathways don't run amok and get too crazy and activated. It's involved in sleep, and again, it's the major inhibitory neurotransmitter. Now, it's well known that anyone who takes progesterone as a hormone replacement strategy quite often experiences a calming effect. They commonly experience an increase in their deep REM sleep and how restful their sleep period is. And part of this is because there's a bidirectional relationship between progesterone and GABA, such that having adequate GABA improves your progesterone receptor responses, and having adequate progesterone improves your GABA function. And then finally, there's a functional relationship between testosterone and dopamine, such that having adequate testosterone helps your dopamine work better. Having good dopamine levels affects how your testosterone or your androgen system works. And so I'm just going to go through that list one more time, and I'm not going to go into the functionality of it. But basically, thyroid sensitizes all neurotransmitter receptor systems. There is a bidirectional relationship where estrogen and serotonin are mutually supportive. There's a bidirectional relationship between progesterone and GABA in which they are mutually supportive. And there's a bidirectional relationship between testosterone and dopamine in which they are mutually supportive. And so don't always blame continued hormone symptomatology on not being on the right dose if you're taking hormone replacement therapy. Or maybe, thinking that if your hormone levels were in the upper third of the reference range rather than the bottom third, maybe that's, what the difference is. Sometimes it's not that system. Sometimes it's these heterotropic modulators that are outside the system that are affecting how that system works. Now, the final thing to talk about here, because we're focusing on neurotransmitters and the role that they play, it's very, very common in the functional medicine world, the integrative medicine world, as well as demand from healthcare consumers to want to have a doctor test their urinary neurotransmitter levels. This is a model, a clinical model that has been around for, I'm going to say, probably close to 15 years, if not more than that. Obviously, the technology's been around for longer. And so it is quite valid to say, yes, we can measure neurotransmitters in your urine. That's very well established. What is not established, and what is quite factually incorrect, is to think that you can pee in a cup and measure your neurotransmitters and assume that that has anything to do with what's happening up in your brain. And this is, when I've taught a course on brain health or brain chemistry and nutrition, or what we call our Mastering Brain series, one of the very first things that we start with is, hey, docs, let's make sure we're all on the same page. You can't pee in a cup and measure neurotransmitters and assume that you know what's happening in the brain. And here's the reason for that. While you can measure serotonin, dopamine, GABA, acetylcholine, and all the major neurotransmitters in urine, most of these do not cross the blood-brain barrier. In fact, all the ones that I just listed do not cross the blood-brain barrier, with the exception of acetylcholine. And the brain makes its own neurotransmitters. Yes, there are some neurotransmitters made, for example, in the gut or by the adrenal glands, things like epinephrine or norepinephrine, even things like histamine or phenylethylamine. These can cross the blood-brain barrier, but that's the exception rather than the rule. When it comes to the major neurotransmitters that run most of our major neurological pathways, again, serotonin, dopamine, GABA, and, for example, acetylcholine. And I have to correct myself. I misspoke saying that acetylcholine crosses the blood-brain barrier. To my knowledge, it does not. It's just that the brain very easily makes its own acetylcholine. We'll come back to that in just a second. All of these major neurotransmitters that basically run most of your brains. Your brain makes them. It makes it from precursors from your diet that obviously come in through your GI tract, get absorbed in your bloodstream. The precursor amino acids get into the brain via different, either mostly active transport mechanisms involving things like large neutral amino acid transport molecules. And once these amino acid precursors are inside the brain has its own metabolic machinery to make serotonin, to make dopamine, to make acetylcholine, to make GABA. And also it makes its own catecholamines or epinephrine, norepinephrine, even though those made in the body can actually cross the blood-brain barrier into the brain. But again, that's the exception rather than the rule. And so if you or anybody you know has ever had a urinary neurotransmitter test, and they're like, well, see, my serotonin is low, so I need serotonin for my anxiety, or I need serotonin for my sleep patterns, or whatever the case might be. Understand that serotonin, the vast majority of serotonin is made in the gut. In fact, I would tell you that if you pee in a cup and some lab says, here's the neurotransmitters that we found, you're looking predominantly at gut physiology and gut health, and you're not looking at the brain. In fact, let me tell you just a real quick story. This was back when I was practicing in the Sarasota area of Florida many, many years ago. And I had a lady who I'd worked with before, and she had done very well, and she disappeared, as people who feel well do. They don't feel the need to come see people like me. And it was a year or two before I heard from her again, and she called me almost in a little bit of a panic because she had seen a local practitioner, another type of practitioner, who had done this neurotransmitter test on her and had given her some supplements to change her brain chemistry. And it really made her a lot worse. And so she came into my office with a stack of labs, including the neurotransmitter report. And as we were talking, I was flipping through the labs to see what was available to me. And I took the neurotransmitter report and put it off to the side because I wanted to point out to her when the moment was right that, this is not really valid information. We can't do anything with it. And she looked at me, she got a little bit confused, and she took it off the spot where I'd put it on my desk, and she put it back on the pile that was right in front of my hands. She wasn't being disrespectful. She was just frustrated, and she was desperate. And she said, you need to look at that. And I said, well, I'm actually quite aware of this particular lab as well as this technology. And, unfortunately, it's not really valid testing. It doesn't tell us anything about the brain. And so we had this conversation, and she ended up being unfortunately quite deflated because she had spent a lot of time and money with this other practitioner only to get worse. And she, of course, wanted me to fix her brain, and she wanted me to use this neurotransmitter report to do that. And I explained to her in simple terms that it's just not possible because you can't connect the two. And so the interesting thing was I held on to those because I wanted to scan them into my electronic record system. And it turns out right on the bottom of the first page, the lab had this CYA statement that says, and I'm paraphrasing here, but you get the idea, something like, oh, by the way, you can't use this to make any assumptions about brain function. Because even the labs that do this type of testing and actually promote a clinical model of testing urinary neurotransmitters for the purposes of understanding brain function, even they know you can't do that. And there was a statement right on the report itself in big red letters that actually said that very fact. And she didn't pick up on it. Clearly, the practitioner that she had been working with before she came back to me didn't pick up on it. So anyways, things turned out quite well for her. We kind of went back to some basics, and she had gotten off her diet. She had lost stability of her blood sugar, and those are two massive keys for neurotransmitter balance and control, is diet and blood sugar stability. But nevertheless, the whole point is to make sure that you understand, as you listen to this, that if neurotransmitter function is something that is of interest to you, and someone comes along and says, or if you discover it in your own research, that there's a way to test neurotransmitters in your urine, don't do it. Don't bite. It's a trap. It's a trap because there's no clinical correlation between the two. Most of these things that you measure in urine reflects gut function because that's where most neurotransmitters are made. And the brain makes its own. It makes its own serotonin, dopamine, acetylcholine, GABA, epinephrine, norepinephrine, and so on, and so on, and so on. And of course, there's no way, if you look at research, and these studies are all done in animal models, we're not going to take a human and sink a needle into their basal ganglia to measure their dopamine. We're not going to go into the frontal lobe in the premotor cortex or the prefrontal cortex and measure serotonin and dopamine. Or we're not going to go to the frontal lobe in general and take a look at the catecholamines. Which brings me to the last thing that I want to touch on as it relates to neurotransmitters, and understand that I'm just kind of giving you a primer on neurotransmitters because we've already mentioned and established that neurotransmitters and hormones work together. It's very easy for us to assess hormone balance. It's very easy for us to assess free fraction hormones, biologically available hormones, or biologically unavailable hormones that are protein bound, and to put that into kind of a systems view. What we can't do is, from a laboratory diagnostic perspective, we can't measure neurotransmitters unless we pee in a cup, and that's just about the gut. It's not about the brain. And I hope I guess I beat that horse a few times, so we'll just leave that alone. So what are we left with? Well, there's a whole field of research called neuropsychopharmacology. And it turns out over many, many decades, they have done either nutrient depletion studies, where, for example, they might take all the tryptophan out of a diet to see how depleting serotonin, and that's the precursor to serotonin production, but just to see what it's like. Like, if you can't make serotonin, what does that look like? Like, how is your thought process? How are your emotions? Does it affect your sleep patterns? And we have this, turns out that we have a fairly robust description of what it looks like and feels like to have bad serotonin or low serotonin, or to have low dopamine. And again, they used nutrient depletion studies, so animals in these trials can't make sufficient amounts of the given neurotransmitter that's being studied, or they use some kind of chemical to block the neurotransmitter receptor sites. And so you can get to a lack of function one of two ways. You can either change the amount of neurotransmitter that's in the environment, or you can change how the receptor responds, right? And so what I'm going to do, and as I close this out and close out this little mini series, and we'll move on to something else in the next episode. So I just want to give you a couple of things to think about if you're wondering, like, hey, I wonder if I have a problem with serotonin, or I wonder if I have a problem with GABA. And there's more to the picture than what I'm going to describe here, because I'm going to try to do it clearly but fairly quickly. Understand that what I'm giving you right now tend to be the hallmark symptoms or presentation. So while I say, for example, that with serotonin, quite often what we see is what we call a guilty depression, and certainly we can see changes in sleep patterns. That is the hallmark. That's what we see most commonly with serotonin, but there are other things that might be related to some kind of serotonin deficiency or serotonergic dysregulation. So, number one, serotonin quite often results in a guilty depression or changes in your sleep quality. What does a guilty depression mean? Well, it means that somebody can recognize that they really have no reason to feel depressed, but they still feel depressed, and they actually feel bad about feeling depressed. That's a classic serotonergic type depression. Now, you can have depression from changes in dopamine. You can have depression from changes in catecholamines. But if you look at the neurological literature, depression is first and foremost characterized as a neuroinflammatory issue, not a neurotransmitter issue, even though that can be involved as well. And so if somebody comes to me and they're asking for help, in fact, I just finished doing a consult with a gentleman down somewhere in Florida, and depression is part of his picture. And so my first thought is, well, I wonder where the neuroinflammation is coming from. My first thought is, well, he probably has a serotonin deficiency. That's not my first thought, because physiologically that's not the primary cause, right? So depression generally as a rule is neuroinflammatory rather than neurotransmitter, although you can have both at the same time. So serotonin, guilty depression, and poor sleep. What about dopamine? Well, you can have depression with dopamine as well, but somebody with dopamine type depression can go out and they can kind of enjoy life, go out with their best friend, go to a movie, have a nice meal, and they enjoy it. But then when they come back home, they're depressed, as opposed to that guilty depression of serotonin, where somebody just kind of has lost all zest for life. You know, their best friend calls and says, hey, let's go see a movie and grab some food. And they're like, nah, I don't really feel like it. That's, again, how we might be able to differentiate different types of depression just based on these studies in neuropsychopharmacology. So dopamine, lack of motivation, lack of self-worth. It's just like, I just don't feel like doing stuff. Like, I don't have any goals. I don't have that, go get it attitude. And very common with dopaminergic issues is kind of like a tendency to get angry very easily. Like probably most extreme example could be something like road rage. But, quite often you'll have somebody who gets upset with just inconsequential things, either things that never used to bother them starts to bother them, or people get upset over things that nobody else gets upset over. That's quite often associated with dopamine type issues. The GABA picture is pretty classic and it's very consistent. And we'll see things like anxiety, insomnia, and in some cases, some degree of OCD or obsessive compulsion disorder. And that might manifest just simply, not the form where someone is like, counting their light switches or getting out of bed to make sure every single lock is in the lock position. That, again, would be a more extreme example. But sometimes the mild OCD type tends to show up as just being very fastidious. Everything's just got to be in its place. And if something's not in its place, kind of feel compelled to go fix it. That's the difference when we're dealing with someone who's just neat and orderly and tidy versus someone who has this mild form of OCD. It's the lack or the presence of that compulsion. Something's out of place. I must go fix it. That is, again, more indicative of an OCD type issue. So GABA, quite often we see the anxiety, and that should make sense because GABA, as I just described it, is your main inhibitory neurotransmitter. And the brain predominantly is excitatory. No, actually, no, I should say it the other way. The primal brain is predominantly excitatory. That's why our heart beats all the time. And, that part of the brain which is rooted in your brainstem, is designed to be constantly active and to keep you alive, which is a good thing. But as the brain develops, the vast majority of the cortex, the higher brain, is actually inhibitory in nature, and GABA is what runs most of that show. And there certainly are other inhibitory neurotransmitters, but GABA is the most prevalent one. And so if you have a problem with GABA, you tend to lean more into an excitatory phenotype, which means basically you're looking at things like being nervous or anxious or jittery. And because GABA is part of our calming system, it is also the main neurotransmitter that runs the neurological network that controls sleep. And sleep is both Now, I should say not both. It is all neurotransmitter-based, hormonal-based, as well as immune and inflammatory-based. It's a very complex system, which is why sometimes it's difficult to figure out, where the sleep issue is coming from. But that's GABA, anxiety, insomnia, and some type of OCD. Then we have acetylcholine, which again, does many, many different things, but it's intimately involved in learning and memory. And also, just kind of as an aside, acetylcholine is the main neurotransmitter used in the neural network of what's called the hippocampus, which is involved in controlling your adrenal circadian rhythm. And that's another functional pair that I failed to mention earlier, is that acetylcholine and the control of cortisol is very intimately related. And so with acetylcholine deficiencies or some kind of dysregulation, we can see that lack of short-term memory, kind of living your life with reminders and sticky notes because you can't keep it in your head, not the way that you used to. And also looking at ability to learn and retain things. And I would say this, if you find it harder to learn and remember things now than you did a couple of years ago, you're losing ground, if you will. Now, acetylcholine could be part of that. There's other issues that might cause some type of degeneration, if you will, in your learning pathways. But one of the first things that you can think about is your acetylcholine sufficiency and whether or not there's some kind of homotropic or heterotropic modulation of those receptor sites. And then finally, and this is the last of the 5 major neurotransmitters that run most of the major pathways in your brain, that is your catecholamines, or technically that's 2, that's your epinephrine and norepinephrine, but basically we're talking about adrenaline. And adrenaline is used in the frontal lobe particularly to give us that awareness, that wakefulness, to give us crisp and clear and fast mental processing. And so if you feel like your mental processing is slowed down, if you think that your thinking process, your cognitive process is not as clear as it should be or as it used to be, and if you can't really attend to things and you're losing focus and concentration, there might be something going on with your catecholamine system. Or another way to say it, slower cognition and easy distractibility, which unfortunately is very common in these days. And so what I've done with this list is we've gone through just a little primer on neurotransmitters just for the purpose of talking in the context of how neurotransmitter systems can affect your hormones. And if our focus in the series, as it has been, is to talk about hormones and health, we have to not just talk about hormones, but we have to talk about all the different things that affect how hormones work, which then leads into a discussion of neurotransmitters, the different types. Can we measure them? Can we not? What does peeing in a cup have to do with neurotransmitters of the brain? The answer is nothing. And then at least having a brief description of how serotonin, dopamine, GABA, acetylcholine, or catecholamine deficiencies can manifest in terms of a symptom picture. And then at that point, we can decide, does it make sense to supplement with things like amino acid precursors or other compounds that the literature has shown us can actually modulate the system and improve it. And with that, we're going to close out this episode and close out the mini-series focused on hormones and health. As always, like, follow, subscribe, do all those things related to thumbs up with the social media. And thanks for being part of the Inflammation Nation. We'll talk to you at the next episode and with the next mini-series. Take care. Thank you so much for listening to the Inflammation Nation. If you found this episode valuable, please rate, review, and subscribe to our podcast. Be the first to know when a new episode drops so that you can stay on top of your game. It also helps others like you find the answers they need. And why not head over to my main website, drnoseworthy.com, that's drnoseworthy.com, to explore my personalized functional medicine coaching programs, submit a question to the podcast, maybe take a quiz, or even reach out to me using the contact form that you can find there. We'll see you next time.